Welcome back for chapter 14. It's going to be a relatively short chapter. We're going to talk about acids and bases, what makes them different, what kind of chemistries they have, and where you find them in your everyday life. So let's start out here just talking generally about acids. So acids, if you were to taste them, which you should never do in the lab, but if you were to taste an acid just in your everyday life, which you do all the time, actually, they tend to have sour tastes. This is one of the things that gives fruits like lemons their sour taste. They're actually decently acidic. Acids are also very good at dissolving metals. This is why acid rain can be such a big problem, because it can erode metal structures. As well as lots of stone structures as well. Acids also turn blue litmus paper red. So if you have a piece of blue litmus, like this right here, if you stick it into an acid, it will turn the litmus paper red as a result. And you will see this in at least one of the labs that we're going to do. We'll be using some litmus paper. A few different common acids that you'll come across, mainly just in this class. You don't come across these too often in your everyday life, but sulfuric acid is a relatively well-known acid. It is a very strong acid, as is hydrochloric acid. Hydrochloric acid is actually fairly often used in toilet bowl cleaners. Sulfuric acid is used in car batteries. And then you have acetic acid as well, which is a much milder acid, but still something you wouldn't want to get a whole bunch of really concentrated acetic acid on yourself. But if it's very dilute, we just call it vinegar, and we eat it on our salads. So that's acetic acid. Bases, on the other hand, tend to have a very bitter taste. And again, we're not going to be tasting anything in any of the labs that we do. But bases do tend to have a bitter flavor. If you get a base, especially a strong base, on your hands, they will feel slippery. What's happening there is actually a saponification reaction. The base actually starts to turn your skin into soap, and that's why it starts to feel slippery like that. It turns red litmus paper blue, so it's just the opposite of acids in terms of what it does to litmus. And a few common bases are sodium hydroxide. It's a pretty common one, actually. Thankfully, we don't deal with it too often in our everyday lives because it is pretty nasty. But it's used in a lot of industrial situations. Ammonia is used relatively commonly, actually, as a cleaner nowadays, but it is a base. And then sodium bicarbonate, otherwise known as baking soda, is also a base, although a weak one. So, we've talked about acids and bases here in the last couple slides and given a few examples of them, but we haven't actually said what makes an acid, what makes a base. We just know that they are kind of opposites of one another and they react with stuff. So we're going to look at a couple definitions here. There's more than just these two, but these are the two most common ones, especially in lower level chemistry classes. If you were to take graduate level chemistry classes, you'd learn different definitions, but we're going to stick with these two. And these are the Arrhenius definition and the Bronstedlowry definition. The Arrhenius definition says that acids produce H+ ions when you put them into water in aqueous solution, and bases produce OH- ions in aqueous solution. So, to put it another way, if you stick a molecule into water, and as a result of that, you get more what we call hydronium ion is the technical term, but essentially you get H+ in solution, well then that thing is an acid. And for a base, if you put a molecule into water and it produces OH- in solution, well then that is a base. So essentially we're making this definition based off of the effect that the molecule has in water. That's where we get that definition. One quick thing about H+, the hydronium ion. When we put acids into water, technically speaking, they don't actually make H+. H+ is actually just a proton. That's all that would be. It's just a single proton. And that's not stable enough to just be floating around in solution all by itself. So instead, what actually happens is it forms H3O+. So that H+ ion attaches to a water and gets carried around by it, essentially. But just for sake of simplicity, we usually just call it H+, and it's just kind of understood that when we say H+, we actually mean H3O+. So if you see it in the book, or if you're doing some research online or something, and you see people referring to H3O+, and you're really confused, like, what? H3O+? We talked about H+. They're used interchangeably. Alright, when it comes to the bases, on the other hand, it really is just OH- floating around in solution. So if you put sodium hydroxide, for example, into water, it really does just break apart into sodium plus and OH-, and so you get OH- in solution because of that. So there's no shorthand there. It really is just hydroxide ion. That's what we would call that. Okay, so this first definition, the Arrhenius definition, it works really well in a lot of the cases, in pretty much every case that we're going to be looking at, because we use water all the time. But when it comes to certain other molecules, the Arrhenius definition doesn't quite work because, again, number one, it's closely attached to water, and there are molecules that will behave in acidic fashion or basic fashion not in water. And then there are molecules as well that, for example, will produce OH- in solution but actually don't have any OH in their structure. And so to kind of expand the definition of acids and bases, we have what we call the Bronstedlowry definition. And the Bronstedlowry definition says that an acid is a proton donor and a base is a proton acceptor, or H+ acceptor. Because again, remember, an H+ is just a proton. If you remember back from earlier chapters, hydrogen is just one proton and one electron. That's all you have in hydrogen. And so if it's H+, that means that the electron is gone, and so it is just a proton. That's all that's left. So, if we were to look at that Bronstedlowry definition again here, for example, in reference to ammonia, NH3 is a classic example of a Bronstedlowry base. It has no OH- in its structure, but when you put it into water, what happens is the ammonia, some of them, not all of them, but some of the ammonia molecules will pull an H+ off of the water to form ammonium, which then leaves OH- in solution. And so when you put ammonia, NH3, into solution, it produces OH-. So that is it's behaving like a base in that sense. And so we would call this a Bronstedlowry base. Now do keep in mind that anything that is an Arrhenius acid or base is also going to be a Bronstedlowry acid and base. So we have the Arrhenius acids and bases. The Bronstedlowry acids and bases are going to include all of those Arrhenius acids and bases. We're just going to add in extra, essentially. It's covering more molecules. But everything that would be in Arrhenius would also be Bronstedlowry in terms of definitions. Acids, kind of the same thing here. HCl, which was an Arrhenius acid, it is still going to be a Bronstedlowry acid and base, because in this case here we have the HCl, and it is donating the H plus to the water. And so you end up with H3O plus and Cl minus. So it is still acting as an acid, just under a slightly different definition. Now you might have noticed on this last slide here, the water acted as an acid in this Bronstedlowry reaction because the ammonia accepted a proton from it, which meant that the water was donating a proton to the ammonia. But then in this one, the water was acting as a base because the HCl was donating a proton to it. And this actually happens all the time. There are actually lots of molecules. Water is by far the best example. But there are lots of molecules that under certain situations, they will act like a base. And in other situations, they will act like an acid. It just depends on what else is around and whether that other thing that is around is a stronger acid or base than water is. We call these kinds of molecules amphoteric substances. They're also sometimes called amphoteric substances. I'm not sure why we have two different names for the same thing, but just for the sake of clarity, I wanted to let you know about both of those. So, in every single one of these reactions, we will have an acid and we will have a base. Those are required. We cannot have a reaction where something acts as an acid and there is not a base. By definition, if something is donating a proton, something has to be accepting it. You can't give a present to someone without someone to give a present to, essentially, to use an analogy there. There has to be something to accept the proton. So you will always have an acid and a base. And as I mentioned just briefly a second ago, as it says here, and it doesn't explain it terribly well here, but it says, in many cases, the acid or base would not be considered an acid base under normal conditions, but will act like an acid or base when it is reacting with a strong acid or base. So water, again, is a good example of this. You know, we drink water all the time. You know, it's not strongly acidic or basic, but if something else comes along, like HCl, in the previous slide there, the HCl essentially forces the water to act as a base. The HCl's big strong molecule, so to speak, again, just using an analogy here, big strong HCl comes along and says, hey, water, take this, and just essentially forces the water to take the extra proton. The water wouldn't necessarily just go up to another water and pull one off. It is actually possible to do that, but it doesn't happen terribly often. But if the HCl comes along and forces the water to do that, well, then it will. It just, again, it depends on what else is around. If there's a strong base around, the water will act as an acid. If there's a strong acid around, the water will act as a base. It just is dependent on the situation. Okay, let's look at example 14.1 real quick from the book here. It says, in each of these reactions, identify the Bronstedlowry acid and the Bronstedlowry base. And let's see, we'll write these reactions down real quick here. We have H2SO4. It is reacting with water to produce H3O plus and HSO4 minus. So in this particular reaction, well, I'm not going to give you the names of the molecules, or I'll give away what they are. If we look at what we have going on here, we have a sulfur molecule on both sides, and we have a water or water-like molecule on both sides. So if we look at the sulfur molecule, it starts off H2SO4. Over here we have H SO4. The difference is that from the left, from the reactant side to the product side, we have lost H+. This has given an H+ to the water. And if you remember, according to the Bronstedlowry definition, whatever is donating a proton, that is the acid. Which means by definition, this must be the base. And that is what we see in the reaction as well. The water is accepting a proton, accepting an H+, which makes it the base. Now the question also asks us to find something that we haven't discussed yet, and that is the conjugate acid and the conjugate base. The conjugate acid and base are going to explain it in the simplest way possible, whatever is the acid in the forward reaction is going to be the conjugate base in the reverse reaction. And whatever is the base in the forward reaction becomes the conjugate acid in the reverse reaction. So if this reaction were to go backwards, essentially, if we were to go back to where we were before, this thing, this is called bisulfate, by the way, this would act like a base. It would accept back the H+ from the hydronium, and the hydronium would act like an acid. It would give back that H+ to the bisulfite. So if you're asked to find the conjugate acid or the conjugate base, just whatever that thing was in the forward reaction, it's the opposite in the reverse. Because the reverse reaction, everything is just flipping. Whatever was giving up is now accepting, and whatever was accepting is now giving up. Okay, let's do one more real quick here. So this is HCO3 minus, also reacting with water, and H2CO3. And we end up with OH minus in solution. And all of these are in aqueous phase, by the way, except for water, obviously. It's just a liquid. But I'm just saving myself a little time, not writing them in. So what I would like you to do is pause the video and see if you can work out what's the acid, what's the base on the left, what is the conjugate acid, and what is the conjugate base on the right. So go ahead and pause the video now. Alright, so once again, if we look at what we have going on here, we have a carbon-based molecule on both sides, and if we look at what happens to that molecule, on the left we have HCO3 minus, on the right we have H2CO3. The difference is that this molecule has gained H+. It now has H2 instead of just H. And it was negatively charged before, and now it's neutral. So it's gained H+. So because this has gained H+, it has accepted a proton. This is our base. Which means that the water should be acting like an acid. And if we check what happened to the water, yes indeed, it did donate an H+. It went from being H2O to OH minus, so it lost an H and a plus charge to become OH minus. So it is indeed our acid. And so just like in the previous example then, when we're trying to find the conjugate acid and conjugate base, all we're doing is really just figuring out, okay, if the reaction were to go backwards, what would be acting as the acid and what would be acting as the base. And it's really easy as long as you know one side, just whatever this molecule is on the left, what it becomes on the right is going to be the opposite. So this would be our conjugate acid, and this would be our conjugate base.